All right, we'll go and get started. Couple things first. I hope you read the email I sent all of you. Um, this class really only works if people participate in it. Okay, and what I mean by that is that in order for this, in order for you to get as much of this, as much out of this as you possibly can, there are three things you have to do. Okay, and I laid this out very clearly in the email. I also laid it out very early on when we did this. Okay, you go to on campus, you respond to the prompt. Okay, that's there for me so I can gauge what questions you guys actually have. Okay, then you come here. Then after the lecture, after I go through all of this stuff, you go to Teams and I can help you on a more individual basis. Okay, so even if you don't have any questions, it's good to be in there. It's good to be in the call. So when people do have a question that you're not too sure about, you can listen in. Okay. Uh, if you're responding without even trying the homework, it's not helpful. Okay. So if you're saying none, yes, that's answering the prompt, but it's not really doing a whole lot for anyone. Okay. You and me, but also like the entire class. Okay. So for one, we need to actually be caught up on the homework, which I'm only giving you like one of these a night. Okay. I gave you two last night, and I get that that's a little bit more, but I'm trying to be also flexible with when I actually put these in. Right. So if you need more time, you need to let me know. Today, what I want to do is I want to quickly review the sum of a finite geometric sequence. All right. And there are a couple of questions in on campus, which I'll try and answer. And then I want to go over the sum of an infinite geometric sequence. So we just have one more equation, you have one more piece of homework, and you're just applying that equation. That's it. Okay. So one question, I think someone just wanted another example of the sum of a finite series. So I'm going to take one from around, say, the 60 range. Okay, so we want to take the sum from 1 to 11 of 5 times negative 1 to the power of n minus 1. All right. So our equation for this is the first term times 1 minus our common ratio to the power of n over 1 minus the common ratio. Now for this equation, we have to remember that n isn't necessarily the upper limit. It's the number of terms we're summing together. So in order to get from 1 to 11, right, there are 11 terms. Our common ratio is whatever's attached to the exponent. So in this case, it's negative 1. And then in order to get the first term, we simply plug in our lower limit into the equation, and we get our first term. Okay, so that ends up being 5 times negative 1 to the power of 1 minus 1, which is 5 times negative 1 to the 0 power, so it's just 5. And then we plug all that in and get an answer. Okay, so the sum of these 11 terms is 5 times 1 minus our common ratio to the power of 11 over 1 minus our common ratio. We plug that in into a calculator and get a number. So negative 1 to the 11th, that's just going to be negative 1. So 1 minus 1 is 0. So we get 5 times 0 over 2. So this just ends up being 0. And that's it. Okay, once we get a number and we simplify it, that's our answer. Now, say for example, this lower limit started at 3. Okay, our A1 would change. So instead of plugging 1 into our exponents, we'd plug in 3. And then the same goes for this exponent up here. Okay, instead of plugging in 11, we'd have to do the terms from 3 to 11. All right, so it'd be 8 instead. Okay, and then another question was, well, first, are there questions about that example? Okay, from this example, we have to pull out several things. We have to pull out the common ratio, which is the easiest thing to do, right? It's the thing attached to the exponent. So in this case, it's negative 1. R is equal to negative 1. That's it. Just stop there, right? Step 2, find how many terms we're actually adding together. So that's n, okay? For n, we count from our lower limit to our upper limit. So there are 11 terms in total. That's it for step 2. For step 3, we find our first term. In order to find our first term, we plug in our lower limit into our equation, right? Which I did right here. Then we plug those numbers in to our equation and we get an answer. Okay, and the next kind of type of question that people were having is how can a sequence be both arithmetic and geometric? And if we just have a constant, we have to think about what this actually means. All right, so if we write all of the terms out, or the first couple of terms out, what we're doing is we're substituting in 2 for wherever we see n into our sequence. Okay, but there is none. So our first term is just 22. Right, so this is when n is equal to 2. When n is equal to 3, right? We plug in n is equal to 3 into this equation, but there is nothing, so it's just 22 again. This is the second term in our sequence. If we plug in n equals 4, again, there's no n, so we just get 22 out again. And it repeats like this infinitely. Okay, so our sequence is just 22 over and over and over again. Now, for an arithmetic sequence, in order for a sequence to be arithmetic, the difference between terms has to be constant. Okay, so if we take the difference between sequential terms, right? So if we take A2 and A1, and then A3 and A2, it's constant, but it's also 0. So in this sequence, we are just adding 0 over and over and over again. So technically, it is arithmetic. For geometric, in order for a series to be geometric, the ratio of two sequential terms has to be constant. Okay, so we would take the ratio of A2 to A1 and the ratio of A3 to A2, which again, they're just all 22. This ratio will be constant, and it will be 1. Okay, so because it's constant, it's also geometric. So this example is both geometric and arithmetic. Okay, so whenever you get the sum of a constant, which is exactly what this is, it's going to be both. Questions about either of those two things? Okay. If you have further questions about either of these two homeworks, you can save that for after. All right? Because we have one more thing to cover. All right. Um, so save that for teams in a meeting later. I do want to talk a little bit about your final. Your final is probably going to be a little bit like the last test, okay? And it will only cover this content, and we might cover like one small thing next class period. Okay, then and after that, we'll start to review for the test, and it'll be kind of like a worksheet. You do it. I'll give you a 2-hour period to do it. Fill it out, take a picture, and then I'll grade it. Okay, so that'll be your final. All right. I don't think we have enough content to do an actual project. I think we kind of ran out of time with all this going on to get to real probability, and we don't have enough kind of to make this interesting, which is okay. But it's still getting to like that beginning of calculus type stuff. Okay, so today's class, quickly, I want to just review this for a second. So most of this homework was about the sum of a finite geometric sequence. Okay, so we have this equation, the sum of a sequence of a geometric sequence that's finite. We can solve by using this boxed equation. All right, and keep in mind that the exponent, that's the number of terms we're solving for, and a1 isn't necessarily the first term of the sequence, but it's the first term that's being added. Are we going to get a practice test with answers on it to go over it all? Yes, I will give you some type of review like that. All right. And then besides this equation, all right, we went over a couple of examples. I'm not going to go over them right now, but really it's just about pulling out numbers, naming them, and then plugging them back into the equation in the appropriate spot. Okay, and that is summing a sequence that is geometric. All right, today, as opposed to finite, I want to go over infinite geometric sequences. Okay, so an infinite geometric sequence is a sequence that has a first term, a second term, a third term, a fourth term, but then it keeps going without end. So it does not stop. And when you have a geometric sequence that does not stop, and the common ratio is between 0 and 1, we get something that we can sum. And the sum of an infinite geometric sequence, whose common ratio is between 0 and 1, can be evaluated with this equation. Right, so it's the first term of the sequence, or of the sequence that we're adding, over 1 minus the common ratio. All right, and we're able to do this because when you multiply numbers by something between 0 and 1, it gets smaller and smaller and smaller. So a sequence like this is said to converge at a certain number. Okay, so when this is true, when r is between 0 and 1, the sequence converges. Okay, when r is greater than 1, the sequence diverges. So for example, if I have the sum from n is equal to 0 into infinity of 4 times 0.6 to the power of n, we can sum that infinite sequence by using this equation. All right, so there are two things we need. We need the common ratio, and we need the first term of the sequence. So the common ratio should be really easy to get. All right, this is always the thing attached to the exponent, kind of just like the last couple of examples. So in this case, it's 0.6. And because this is less than 1, we can sum this infinite geometric sequence. All right. The second thing we need is the first term. Right? And we can get the first term by plugging in our lower limit into our sequence. And when we do that, we get 4 times 0.6 to the 0 power, which just equals 4. And then we take those two numbers and we plug them into our equation. So we get that this sum is equal to our first term, which is 4, divided by 1 minus our common ratio. And then we evaluate that on a calculator. So if we take 4 and divide that by 1 minus 0.6, we get 10. And 10 is our answer, right? So that is the sum of an infinite number of terms. But because that common ratio is less than 1, it converges to a single number. So I'm going to stop there for a second. Are there questions about this example? Can you go over how to get A1 again? Yeah, the first term that we're adding is always going to be, you take this lower limit, right? N is equal to 0, and you plug it in to your sequence. That's it. Plug your lower limit in, and you'll get the first term that you're adding. How does it equal 4? Because 0.6 to the 0 power, that just simplifies to 1. So this is 4 times 1, which is 4. All right, a second example, we're not necessarily explicitly going to be given every single thing we need. Sometimes we have to find the common ratio and just look for the first term. Okay, so we are given that this is a geometric sequence, which means that the ratio between two consecutive terms is always going to be equal, right? So 2 divided by 5 will equal 2/5 divided by 2 will equal 2 over 25 divided by 2 over 5. Okay, we don't need all of those. They're all constant. We know that because it is a geometric sequence. So we're just going to worry about the first one, right? So let me rewind for a second. In order to find the sum of an infinite geometric sequence, there are two things we need. We need the first term, and we need the common ratio. Once we have those two things, we plug it into this equation. Right, so for this sequence, the easiest thing to get is the first term. It's just the first thing being added. So A1 is just 10. our common ratio, because we know it's geometric, we can just take the ratio of the first two terms. So that'd be 2 over 10, which is equal to 1/5. Right? That's the ratio of the second term to the first term. And then once we have those numbers, we just plug everything in. So S will equal A1, which is 10, over 1 minus our common ratio, which is 1/5. When we simplify this, we get 10 divided by 4/5, which is really 10 times 5 over 4, which simplifies to 25 over 2. Questions about this example? Can you change 1/5 to 0.2 to make things easier? You can, uh, but in the homework you will be asked to give it as a fraction. Some of the time you'll be asked to give it as a reduced fraction, which you can also do that on a calculator just by hitting mathfrak. So yes, but it's also helpful to be able to actually do that. Okay, I want to go over one or two more examples. I think I just have one. No, I have two. Okay, again, these types can be a little bit trickier. Okay, so if I have 3 12/5, 48 over 25, and 192 over 125, and we know that it's geometric, we can take this infinite sum by finding the first term and finding the common ratio. Again, the first term is easy. That's just the first term we're adding. And the common ratio, since we know it's geometric, is just 12/5, right? It's our second term divided by our first term. Which is 12/5 divided by 3. So if we simplify that, we get 4/5. Again, once we have both of those numbers, because this is less than 1, we can plug it in to our equation, a1 over 1 minus r. When we do that, we get 3 divided by 1 minus 4/5. Questions about how I got here? Okay, then we simplify. So S is equal to 3 over 1/5, which is just equal to 15. So this entire sequence converges at 15. And it converges because our common ratio is less than 1. What do you do if it diverges? Well, if it diverges, we can't use this, and it's going to be an undefined number. So later on in the homework, it gets to where it asks, does the series diverge or converge? So you look at the common ratio. If the common ratio is between 0 and 1, you say it converges. And then it'll ask, what does it converge to? So you do this calculation. If the common ratio is greater than 1, it diverges. And then that's that. Okay, so in a geometric sequence, if you multiply by something bigger than 1, it just gets bigger and bigger and bigger. And when you add things together that get bigger and bigger and bigger, the total sum goes up until infinity. So it doesn't converge to any number, it goes up into an undefined number. So r less than 1 converges, r greater than 1 diverges. Okay, and I have one more example for you, and that's this. All right, so we want to take the sum from n to infinity of 1/2 to the power of n. And again, there's two things that we need. We need the first term, and we need the common ratio. In this case, our common ratio is very easy to get. It's just the thing attached to the exponent. So our common ratio is 1/2. The first term that we're adding together is when you plug this lower limit into the equation. So when we do that, we get 1/2 to the power of 3, which simplifies to 1/8. And then once you have both those numbers, you plug them into the equation. And simplify. Again, a question that could come out of this is, does this series converge or diverge? Because r is less than 1, it converges. And it converges to 1/4. So questions about this example? All right, that's all the examples I wanted to go over. Again, it was just over infinite geometric sequences. Your homework, which I'll say here in a second. Um, when I give you the homework, what I would rather you do is to go to Teams and start working on that homework. That way, if you do have questions or you do feel behind, we can get you caught up, or I can answer a couple of questions that'll help you out. Okay. So your homework due on Monday is W18. And again, remember this and maybe just another small piece of content. That'll be it, and then it will be preparing for your exam. Okay. So I will leave this open for the next minute or two. If you have general questions, you can ask me here. Um, if not, in the next like 2 or 3 minutes, I'll start a meeting on Teams, and you can ask questions and work there. How many questions on this exam worksheet? I don't know. It'll cover everything we've covered, though. All right. I'll close this. I'll start a meeting on Teams, and I will see you there.